Hello everyone, welcome to another video on statistics, and today I'm starting on a series of hypothesis testing videos. And my first video is based on the chi-squared goodness of fit test. As you can see here, chi-squared goodness of fit test. The definition of the chi-squared goodness of fit test. The chi-squared goodness of fit test is a statistical hypothesis test used to determine whether a variable is likely to come from a specified distribution or not. It is often used to evaluate whether or not the sample data is representative of the full population. The test statistic is given by the following formula: chi-squared, that's carry x squared, stat for statistic, is equal to the sum of all open brackets O sub I minus E sub I all squared over E sub I, where I ranges from 1 up to k. Now k is the number of trials, experiments, or number of groups in which our data are divided, and O is the observed frequency, where E is the expected frequency. Let's look at example number 1. Example number 1 says Mr. Suzio, a senior political leader in a country called Palige, claims that 4 main political parties, namely A, B, C, and D, enjoy the following proportions of voter support in Palige. That's a hypothetical country. Political party claimed proportion of voter support. We have A, B, C, D, and all other political parties combined. Their claimed proportions of voter support are these ones here, up to there. Now, Mr. Mujuma, a statistics practitioner, interviewed 1,000 people across Palige to test Mr. Suzio's claim. And below are the results. Political party, the number of prospective voters. Out of the 1,000 people interviewed by Mr. Mujuma, 420 said they would vote for political party A, 210 B, 150 that's C, 70 D, and 150 all other political parties. The question says, at 10% level of significance, is there sufficient statistical evidence to support Mr. Suzio's claim? Now, this is a typical hypothesis testing question, and any other hypothesis testing question is a six-step procedure. So our solution starts as follows. Step 1, we have to state the null and alternative hypothesis. So null hypothesis, H naught, it's going to be basically a listing of hypothesized proportions according to Mr. Suzio's claim. So P1 for proportion 1 represents the proportion of voters that would vote for political party A, so that's 0.40. P2, 0.25 for political party B. P3, 0.14. That's for political party C. And P4, 0.10 for political party D. And other political parties, as you can see here, it's going to be 0.11. That's P5. P5 will be 0.11. That is the narrow hypothesis, H naught. Now we have to state the alternative hypothesis. The alternative hypothesis, before I come to step number 2, I have to state the alternative hypothesis. So the alternative hypothesis says the symbol obviously is H1. It says, and this is true for any chi-squared goodness of fit test. Please take note of that. It says at least one of the proportions Pi, where I ranges from 1 up to 5 in this case, is not equal to the specified value. At least one of them is not equal to those given numbers. So for example, maybe if P3 is the one we're interested in, we would say maybe P3 is not equal to 0.14. At least one one of these proportions is not equal to the given or indicated values. Now, that is step number 1. We state the null hypothesis and the alternative hypothesis. In step number 2, we have to state the level of significance. Now, in this case, our level of significance, as you can see here, is 10%. We have to state that. And the symbol for level of significance is alpha. So we're going to say alpha is equal to 10%. And what is 10%? 0.10. And in step number 2, we also determine what is known as the degrees of freedom, df, which is always given by k minus 1 in the case of goodness of fit test. K is the number of experiments or groups in which our data are divided, as you can see here, divided into 1, 2, 3, 4, 5 groups. So K is equal to 5. So it will be 5 minus 1, and the answer is 4. So step 2 is completed. We're moving on to step number 3. And in step number 3, we have to determine what is known as the critical value. Now, the critical value is a number or a value that separates the rejection region from the failed to reject region. So chi-crit, chi-squared crit, because chi-squared, we state the level of significance and the degrees of freedom. And this value is read off from the group, from the chi-squared distribution table, which is here. If I lift it up like this, we're moving to the left side here, where we have degrees of freedom up there, and we move down to 4. In this case, it's 4 degrees of freedom. There it is, 4 degrees of freedom. So we move to 4, and then from 4, we move across. From 4, we move across to where it says chi-squared 0.100. That's our 10%. So we must move and stop there. From 4, move across and stop there. That would be 7.78. That is our critical value. I'm hoping that you can see it clearly there. 7.78. That's our critical value. Move from 4 degrees of freedom and move down there, 7.78. So this is exactly equal to 7.78. This is the number that separates the rejection region from the failed to reject region. Right. Rejection region of what? Rejection of the null hypothesis. All right. Step number 3 done. We're moving on to step number 4. Step number 4 is where now we determine or calculate the test statistic, where we use this formula that I showed you on the introduction there, this formula here. But now notice that in this question here, we're given only observed frequencies. These are the frequencies that Mr. Mjuma observed when he interviewed 1,000 people. He observed these frequencies. So we need to determine the expected frequencies from the hypothesized proportions and the number of people interviewed. In other words, if Mr. Suzio's claim is correct, then how many people would we expect out of 1,000 that would vote for political party A, B, C, D, and all other combined? So this is where now we're going to say, we know our formula says chi-stat, chi-squared stat is going to be equal to the sum of all I from 1 up to, in this case, 5, because we're talking about k, and k is 5, 1 up to 5, of O sub I minus E sub I, all squared, all over E sub I. But remember, we have observed frequencies, and then we also have expected frequencies. Let me write it here, expected frequencies, E. So political party A, observed frequency is 420. I'll put it here. Those numbers there, I'm going to copy them here. 420. For party B is 210. For party C is 150. For party D is 70. And other political parties combined is 150. Now, expected frequency. Let me write the formula over here. E sub I equals n sample space times the hypothesized proportion. Now, in this case, sample size or sample space, in this case, sample size is 1,000 people interviewed. You can see it here. That's the value of n. And these are the hypothesized proportions, P1 up to P5. So this one, for A, it's P1, which the proportion is 0.4. So I'm gonna, following this formula here, it will be 1,000 times 0.4, and the answer is 400. For B, it will be 1,000 times 0.25, and the answer is 250. For C, it is 1,000 times 0.14, and the answer is 140. And then for D, it's gonna be, the proportion is 0. You can see it here, 0.14. That was our C, and for D is 0.10. So it's 1,000 times 0.10, which is just 0.1, obviously. And what does this give us? It gives us 100. And finally, for other political parties, what do we get? For other political parties, we get the proportion there is 0.11, and the answer is 110. If you multiply by 1,000, 0.11 times 1,000, we get 110. Right, now we have calculated our expected frequencies, and then we now are able to determine the test statistic. Let's move on to the next page. Now we need to apply, obviously, this formula here. Right, so now we're going to say, let's do the calculation of the test statistic. We're going to say, therefore, chi-squared stat is going to be equal to, observed for A is 420 minus expected 400, all squared over 400, which is our expected. Right, plus the second space there, observed 210, expected 250, all squared divided by 250. Plus, we're moving on to C, observed 150, expected 140, all squared divided by expected 140. We're moving on. D, observed 70, expected 100, all squared divided by expected, which is 100. And then I'm saying plus. We're moving on to the last part there. 1, 2, 3, 4, the last part. Observed 150, expected 110, all squared divided by expected, which is 110. Right, punching this information in the calculator, we get the following answer. So we have 420 minus 400, all squared divided by 400, plus, that's what the sigma notation means. That one there, it means the sum. This one here, the sigma notation means we have to add. So the next part I'm adding, on the second expression there, and I'm saying, open brackets, 210 minus 250 all squared all over 250, and then I'm going to say plus, we're here 150 minus 140 all squared divided by 140, and I'm moving on, plus, I'm here now, 70 minus 100 all squared divided by 100. If you notice, the cursor has become broader now, which means we have to press the equal button. Otherwise, the calculator would not take any more values. Press the equal button and then say plus. Then type in the last expression there. So the last expression is 150 minus 110 all squared divided by 110. Press the equal button, and if you press the equal button here, it's equal to equal button obviously, and SD button there is equal to this is our test statistic is 31.6597 to 4 decimal places. Step number 4 done. We're now moving on to step number 5. And step number 5 is the decision rule step. Step number 5, decision rule. What does it say? It says reject the null hypothesis if the test statistic is greater than the critical value. Now let's draw the chi-square distribution curve. It's a curve that is skewed to the right. Chi-squared over there. Up there we have f of chi-squared. I told you this is skewed to the right. You have this. Like the f distribution, unlike the normal distribution, which is symmetrical. This one is skewed to the right. Now, let us say that our critical value is around that place there, which is 7.78. As you saw here, our critical value is 7.78. It means that to the right hand side, let's shade this part. That is called the rejection region. Rejection region. In other words, if the test statistic falls in that region, we're going to reject the null hypothesis. This side here is the fail to reject region, the unshaded part. Fail to reject region. And obviously, this shaded area here is your alpha, which is 0.10. Now the question is, where do we place this value here, 31.6597? Do we place it before this or after this? Obviously, you can see that this number is bigger than this number, so it will be somewhere far right there, right deep into the rejection region. That's where you're going to have your 31.6597. Clearly, it tells us that this condition here is satisfied, and therefore, what do we do? What is our decision? We reject HO. So our decision then is, since we're going to say, we're still on step 5, since test statistic that is greater than the critical value. What do we mean here? We are saying 31.6597 is greater than 7.78. Because that is true, comma, we reject HO. We reject the null hypothesis. Now let's go to the conclusion then, which is step number 6. Conclusion. This is where we're going to respond to this question here. This question here, which says, at 10% level of significance, is there sufficient evidence, is there sufficient statistical evidence to support Mr. Suzu's claim? So we're now going to say, at 10% level of significance, we do not have sufficient statistical evidence to support Mr. Suzio's claim. And what is Mr. Suzio's claim? That the four main political parties A, B, C, and D enjoy the stated proportions of voter support. The conclusion must be a comprehensive statement, basically answering the question, the last question there. And this is basically a summary of step 5, where we have made our decision there that we reject HO. And what is HO? HO, if you notice, is Mr. Suzio's claim. And what is Mr. Suzio's claim? That these four major political parties enjoy these voter support proportions. And we have found in step 5 that we don't have sufficient statistical evidence because our test statistic falls in the rejection region, and therefore we reject HO. That was our decision. There it is. Our decision was we reject HO, and therefore our conclusion is we don't have sufficient statistical evidence to support Mr. Suzio's claim that the four major political parties A, B, C, and D enjoy the stated proportions of voter support. So this is where I'm going to stop, but I'm a firm and very strong believer in the power of repetition in the teaching and learning of physics, chemistry, statistics, and mathematics. And therefore, I'll come up with yet another video on the chi-squared goodness of fit test so that this concept is well understood and mastered. If you're new to this channel, please subscribe, share these videos. It will give us the impetus, like I always say, and momentum to be able to produce many more videos. And I trust that the pace at which I'm moving is good enough to accommodate everybody. All right, see you next time.